Historically, Lewis structures were used to describe bonding and ultimately bonding around cubes or squares. The issue with that is that a cube, or even better, a square, is a two-dimensional object, and we run into a big issue when we deal with organic chemistry because we're looking at three-dimensional objects. So the classic example we could use would be looking for the Lewis structure, or looking at the Lewis structure, for methane, CH4. And hopefully, you should be able to come relatively quickly to a Lewis structure along these lines. And in and of itself, there isn't anything wrong with this necessarily until we look at the real world. And when we look at the real world, we find that every carbon-hydrogen bond is equal. Okay, meaning they're all identical. There is no difference between them. Okay? So if we go back and look at our Lewis structure, well, if all of those bonds are equal, then we would expect an equal bond distance between all of them. So we could start to go through and look at this. The way we've got it organized is around a square representing our carbon, and we've got 90 degrees between each of those. Well, that makes sense. Then they're all equal. But one of the things that tends to be a little bit less obvious to see is that what is the bond angle between these two extreme hydrogens? You should notice that that is actually 180 degrees. Okay, the combination of both the bonds in between, or the angles in between. That becomes problematic because now they aren't all equal. Okay, we don't have a perfect system. This is where we came up with the valence shell electron pair repulsion theory, okay, among other choices. The idea here was to say, okay, well, we know that these need to be true. So if I'm going to take 4 bonds, and they all have to be equally spaced away from each other, we would use some fancy geometry, okay, which we could say fancy geometry there, and we would come up with a new shape. Okay. The shape that we would necessarily encounter in this case is unfortunately three-dimensional, and we have a three-dimensional shape referred to as a tetrahedron. This is not easy to draw, okay, which makes things a bit more challenging, but we at least attempt to go through and do it, and we modify our structure to show our hydrogens, those being in the same plane, and then we've got a hydrogen coming out at you and a hydrogen going away. Now the bond angle between every single one of these, no matter which one you're looking at, say even these two, comes out to be 109.5. Every single one is perfectly identical. We have something that matches the real world. Okay. This theory kind of blends Lewis structures and layers on this extra idea of the three-dimensional characteristic that Lewis didn't first look at. Okay? There was no need to. We first need to understand the bonds. Okay? And that's what we're trying to get at with our VSEPR. Well, not all structures are going to have 4 groups of electrons equal to each other. We could have switched to, say, BH3. Okay, well, now we have 3 groups of electrons. Well, that's going to generate a different shape. Okay, so the conclusion that came out of VSEPR is that we now need to look at some shapes, and we need to define these, and we need to be aware of what's happening within each of these structures. What are those appropriate bond angles, and do they match what we would expect in the real world? And it turns out, for most purposes, these are pretty darn close to being our steady-state answers. Within this response, we're looking at what's known as the electron pair geometry. This is an important distinction that we'll make now on our next slide. If we were asked to provide the Lewis structure for CH4 and NH3, well, we've already seen our CH4, but we can draw that up really quickly again. And our NH3, we would notice that we have the same electron geometry. Okay. We draw a box around our center atom. What we would be doing is looking to each of the faces of the box and asking ourselves if there's electrons there. So electrons, 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 electrons. There's 4 groups of electrons. In NH3, there's 1, 2, 3, 4 groups of electrons. So we would end up with the exact same shape. So we would predict the bond angle in ammonia, NH3, to be 109.5. which was a relatively straightforward explanation. We adjusted our theory, we looked at it, we came up with a new result, and we test it and we find out it's wrong. Okay? It ends up not being 109.5. It's close, but it's not exactly. So we again had to go through and modify our theory and say, did we make assumptions that were invalid? Okay? That assumption comes in right there. When we're looking at this theory, we are referencing the pairs of electrons on each of those faces, and we're saying that each of those pairs of electrons are identical to one another. Well, in this case, they clearly aren't identical, because this is a non-bonding pair of electrons, and this is a bonding pair of electrons. So very clearly not different, or not the same, which means we're going to get a slightly different configuration, or a slightly different bend in our structures. So what we have to acknowledge is that we encounter different shapes coming out of this that represent our molecular shapes, or our molecular geometry. For those of you that may remember from 151 or perhaps even 130, there's a whole heck of a lot more shapes that are possible within chemistry. For organic chemistry, we tend to live in kind of the happy little system down here. Okay? And as one extra addition, sometimes we'll jump up to the trigonal planar. So you need to be extremely familiar with those shapes and how we generate them. Okay? Once again, use your Lewis structure. Draw it out. So if we were looking at BH3, put a box around your center atom and look at the face of each of those boxes. There are electrons, there are electrons, there are electrons, no electrons. This means I have 3 groups of electrons. I'm looking at a trigonal planar system. Okay. One last little caveat, or that we'll throw in there, is that can sometimes cause some confusion. What happens here? What is the geometry? Whoops. Okay, let's vaguely remember that we're looking at our boxes. Our Lewis structure, which is around a box. What is the geometry around the carbon? Well, one thing that's confusing for students is that we may acknowledge that there's no electrons here, there's electrons here, and there's electrons here. Sometimes people get confused about what to do with that double bond. Okay. I didn't say single bonds or double bonds or ultimately even pairs of electrons. I just said, is there a group of electrons? Are there electrons on that face? Yes. I don't care how many, but they're there. That means I have now 3 faces with electrons, 3 faces, 3 groups. Trigonal planar is the geometry around that carbon. The mistake that I started to make, that I then quickly adjusted from, was that we might end up seeing this structure drawn more appropriately like this. And instead of showing that kind of 90-degree angle that's represented in the first one that we came up with from our Lewis structure. Well, why would we modify our structure? Well, what is the bond angle in a trigonal planar molecule? Well, the bond angle is 120 degrees. So I want to make sure that I draw my structure as close to the real 3-dimensional model as possible. Okay? The closer you are to that model, the more likely you'll be able to interpret the structure correctly. If you start drawing noses and ears and melting clocks, it may look pretty, but you won't be able to interpret it quite as easily. So we're trying to get as close to that 3-dimensional world as possible. So when you draw your structures, take that into consideration. Deal with your Lewis structure, then change and manipulate it to get it into our proper VSEPR models. Okay? The last part of this is ultimately just acknowledging what all of these things are and how do we end up getting to them. That's what this slide shows. It's your big summary for everything. So step 1, draw your box around your center atom and determine the electron groups. So this is our box on our center atom. Look for electron groups. This leads us to conclude our electron pair geometry. Very often we don't care about the electron pair geometry, we care about the molecular shape. So what we then need to do is interpret, do we have bonding electrons or non-bonding electrons? Bonding electrons we see shown as a line. Non-bonding electrons we see shown as dots, or at least that's how I've shown them. We would then follow through to that appropriate category that matches, That would then lead us to our molecular shape. The molecular shape is then going to necessarily lead us to a proper bond angle that we would then have to go through and use as well. You'll notice that there are some question marks within some of these because I'm not positive on them. Don't stress about that. What we need to acknowledge is that as we change the hybridization, or not the hybridization, increase the non-bonding characteristics, that our bond angle gets a little bit smaller and a little bit smaller, and then eventually it goes massive. Okay? And that I will ask you about in a lecture on Monday. So why do we care? Why look at all this? Why is this even relevant? Why do I need to know something about the shape? Well, we look at methane. We could draw it out. We'd be fine. Okay, there it is. Knowing that I have 109.5 bond angles in there is not super important to me. But what happens if I look at a more complicated structure, say cyclobutane? So cyclo, meaning that I have to have it cyclic, and then butane, meaning 4 carbons. If I show all my bonds in there, if we look at our Lewis structure, we'd say, well, fine, cyclobutane, no big deal. Okay? However, that belies certain information. Okay? What information is that? The bond angle in cyclobutane is forced to be 90 degrees. Each of those carbons has a tetrahedral shape. Well, a tetrahedral shape needs to have what bond angle? 109. So just to build cyclobutane, I am taking this 109 degree angle and I am forcing it to be 90. By forcing it to be 90, I am putting energy into the system. That energy is now stored within the molecule of cyclobutane. What does that mean? Cyclobutane is a very high energy compound. Okay? It has a lot of angle strain on it. That strain we could then take advantage of if we were to, say, react it with oxygen in a combustion reaction. Okay? So knowing something about the bond angle would allow us to predict that we have a lot more energy there than if we just had butane, the 4 carbons in a straight line. Okay? Take it a step further. If we look at chloromethane versus a methyl carbocation. Okay? Well, chloromethane, we might not see a whole big deal going on there. Okay? But if we include the 3-dimensional characteristics of it, that chlorine is starting to suck electrons away from the structure, meaning something else could come in and potentially share. Okay? Depending on the bond angles on that back side and what those groups are, maybe that something can't come in. Whereas, what if the chlorine left? Well, if the chlorine just leaves, I would have a positive charge on my carbon. And now, in the planar situation, if we turn this molecule on its side, we have the potential for something to come in and attack either from the top or from the bottom. Well, there's now nothing there to prevent it. So the carbocation we might expect to be a little bit more reactive than, say, its sister or parent compound in the chloromethane. Kind of a neat little observation. Last one that we could look in here is if we tried to compare 2 other compounds. We'll stick with our chloromethane. And we looked at bromomethane. Well, our initial assumptions might be that there is absolutely no difference in reactivity for these. Okay, we've got chlorine trying to take electrons away. We've got bromine, still more electronegative than carbon, trying to take electrons away. But if we now start to bring in this idea of our valence shell repulsion, we can start to add some extra information. Like number 1, bromine is a lot larger than chlorine. By being larger, that bond becomes longer. Well, if the bond becomes longer, what do the hydrogens end up doing? It's a good question. We'll answer that in class on Monday.